Welcome to the class. So in this class, we'll see how to draw shear force diagram and bending moment diagram for a overhanging beam subjected to UDL. So for this, we'll consider a beam of span. We'll consider a beam of span around 8 meter subjected to UDL. Here we have UDL. Then here we have UDL. This shows that the uniformly distributed load which is spreaded over the length of the beam. Here we have point loads. Here we have point loads around 3 kilonewton over here. Here we have 4 kilonewton load. And these two are the reactions, or you can call it as these two are the supports which we have. So a beam is said to be overhanging if the portion of the beam hanging outside the support is called overhanging beam. And the intensities of these loads are, so here it is 3 kilonewton. It is 3 kilonewton. This is 4 kilonewton. This point load is 4 kilonewton. And intensity of this UDL is 2 kilonewton per meter. And intensity of this UDL is 1 kilonewton per meter. And the length of the distance where these loads are acting are 2 meter apart. 2 meter apart. So here it is 2 meter. Again 2 meter over here. This is 2 meter. This is 2 meter. Let us call it as point A, this as B, this as C, this as D here, then here you can call it as E. Now, in the last video, we have calculated the shear force and bending moment diagram for a overhanging beam by considering the forces and moments from the left of the beam, from this side. So in this video, what we'll do, we'll consider forces and moment from the right side, from the right end. For that, first we should understand the sign conversion for shear force diagram and bending moment diagram. First, for shear force diagram, what are the sign conversion we'll write? Like for example, if this was the plane, if this was a plane XX, if I am considering the forces from this end, from the right side, then the upward acting forces we treat as negative, and downward acting forces we treat as positive. Downward acting forces we treat as positive. Upward acting forces we treat as negative. In the earlier cases, in the last video, what we have done, we consider upward acting forces as positive and downward acting forces as negative. Upward acting forces are positive and downward acting forces are negative. When we consider from the left side, from this point A, if you consider forces and moment from point A from the left side, you need to go with this sign conversion. If you consider forces and moments from the right side, you need to consider these sign conversion for shear force diagram. Upward acting forces are negative, downward acting forces are positive. By using this, let's calculate shear forces. Before calculating the shear forces, I should calculate the reactions at the supports. Here we have a reaction RA at the support A. Here we have a reaction at support D, that is RD. So these two I need to calculate. Here we have two unknowns, RA and D and RD. To calculate these two reactions, unknown reaction, I should know two equations. If I know the two equation, I can calculate these two reaction forces. So the first equation is, what we do, we will take moment about any point. For example, moment about A or moment about T or moment, any point you can take. Let us take a moment about summation of moment about E is equal to 0. In the other sense, I am going to fix this. Then here we have RA into this force into the perpendicular distance. The distance is theta. This is the moment. Next, minus downward force 3 kilonewton into the distance is 6 meters. Then we have UDL here. Between A and B, we have uniformly distributed node. So we know how to convert this UDL into point load. That is nothing but like this lower intensity is 1 kilonewton multiplied with the length is 2. The length is 2 meters. So we'll get 2 kilonewton. So this is the load intensity. Like we have converted this UDL into point load. How to calculate? Like this UDL, usually it look like UDL in the sense uniformly distributed load. It look like distribution of load in a uniform manner over a span of the beam. Here, this is the uniformly distributed load on the beam of length 2 meter, on a beam of length 2 meter. So here the loading is uniformly distributed. So it look like a rectangular. So if we calculate the area of the rectangular, so this is the, you can write height, this is the breadth into height will give the area. Area of the this rectangular will give you the load intensity. Area of the rectangular will give you the load intensity. So that is nothing but if you multiply this one, this is height as nothing but 1 kilonewton per meter and the length is 2 meter. So I can write here 1 kilonewton per meter into 2 meter. So this meter get cancels to 2 kilonewton will be the load intensity. In the other sense, we can say this UDL has been converted into point load of 2 kilonewton. So where this 2 kilonewton acts, it acts at the centroid of this area. So here we have rectangular. In the sense it should act at the center of this. It acts at the center. In the sense it acts at a distance of 1 meter. Or you can draw here. Here we have the point load. The intensity of point load is 2 kilonewton. So we converted this UDL into point load. Now we will focus only on this 2 kilonewton. Similarly here between point C to D, between this C to D we have UDL and its intensity is 2 kilonewton per meter and its length is 2 meters. So we need to convert this UDL into point load. How to convert? Again 2 into 2 is 4. So 4 kilonewton, where it acts, this 4 kilonewton acts at the middle of this. In the sense it acts at a distance of 1 meter over here. It acts at a distance of 1 meter. Similarly, it should act at a distance of 1 meter. Why 1 meter? It is like center of this length or half of this length you can call. Again here the load intensity is 2 kilonewton per meter and the length is 2 meter. 2 into 2 is 4. So this 4 kilonewton should act at the center in the sense the middle portion, at the middle in the sense here at a distance of 1 meter. So here we have converted this UDL into point load. Here we converted UDL into point load, This should be 4 kilonewton. This should be 4 kilonewton. I hope so it is clear now. Now we will calculate the moments, or you will calculate the reactions. We'll calculate the reaction. Okay. Here we have written RA into 8. This reaction force RA into 8 by taking the moment about E, RA into 8 minus this 3 kilonewton into 6 meter. Again we have here minus this 2 kilonewton. We have converted this UDL into point load. This 2 kilonewton and distance is 2 plus 2 plus 2 plus 1. So total is 7 meter. Next we have minus this 4 kilonewton into the distance is 6 meter. Next we have minus this 4 kilonewton into distance is 2 plus 1 is 3. Next we have plus, because here we have RD. RD is the reaction force into perpendicular distance is 2 meter. RD into 2. Then we have minus this 4 UDL into point load 4 into perpendicular distance is 1, which is equal to 0. So I can write this equation as 8 RA plus 2 RD minus, if you simplify you will get 64, which is equal to 0. Or you can write 8 RA plus 2 RD, which is equal to 64. This is the equation number 1. This is the equation number 1. Next, this is the equation number 1. We have two unknowns, so I should know two equations. The second equation is like upward acting forces should be equal to downward acting forces. So here in this beam, upward acting forces are these two at the supports. This is RA and RD. So these two are RA plus RD is nothing but upward acting forces. It should be equal to downward acting forces. So downward acting forces are nothing but here we have 2 kilonewton, 3 kilonewton, 4 kilonewton, 4 kilonewton, 4 kilonewton. So together I can write here 2 kilonewton plus 3 kilonewton plus 4 kilonewton, 4 kilonewton plus 4 kilonewton. 2 plus 3 is 5. 5 plus 4 is 9. 9 plus 4 is 13. 13 plus 4 is 17. So RA is equal to 17 minus RD. This is equation number 2. Now if you solve or substitute equation number 2 in equation number 1. If you substitute equation 2 in 1, you get the values of RA and RD. So RA will be 5 kilonewton, RD will be 12 kilonewton. So try to solve this. If you don't understand how to get these values, you comment below so that I can explain. So once we get these values, RA and RD, the value of RA will be 5 kilonewton here, and the value of RD is 12 kilonewton. Once we get this, the next step I need to calculate the shear forces at each point of the beam by considering this sign conversion. What is the sign conversion? From the right side we are considering, like here upward forces are negative, downward forces are positive. This sign conversion we are using. Upward forces are negative, downward forces are positive. From this end we are considering, like in the previous video we have considered from the left side. From this in this video we'll consider from the right side. Now shear force at point E, at this point, shear force at E, which is equal to, at this point, shear force at point E will be, at this point we don't have any point load, but between E and D we have this point load, because we have converted this 2 kilonewton per meter UDL into point load. So at point E we don't have any the load, the forces, we don't have any forces, so it is 0. But whereas in point D, shear force at a point D, in this point, to the right of this, we have 4 kilonewton, and the reaction force is 12 kilonewton. So 4, it is acting downwards. Downwards in the sense, again, it is positive. So plus 4 kilonewton. Next, at point D, we have a upward force, that is reaction force minus 12 kilonewton. Because why it is minus? So here upward forces are negative. So if you simplify 4 minus 12, 4 minus 12, it should be minus 8 kilonewton. Next, at the point C, at this point, shear force at point C. How to calculate shear force at point C? The forces which are acting to the right of this, like what are the forces we have? We have this force, plus 4 kilonewton, plus 4 downward acting. Then upward acting we have minus 12. Then we have this plus 4. Then we have this plus 4. If you simplify, 4 plus 4, 12, 12 minus 12 is 0 kilonewton here. At point C, we have the 0 kilonewton. Again, like what we need to understand here in the sense, like you should know one thing. While we are drawing shear force diagram, we should know if there is a combination of these loading, UDL and point load. Make sure that like while we are drawing the shear force diagram, first we need to consider the UDL, then we need to consider the point. Clear? So from here to here, like plus 4, plus 4, minus 12, plus 4. Like these point loads and UDL give you the result. Like this will give you minus 4, and this 4 is the separate point. So it will give 0 kilonewton. You should know this, minus 4 plus 4. So you will understand this while we are drawing the shear force diagram. Next, shear force at the point, this point. This is point B. Shear force at B will be, like again, plus 4, minus 12, plus 4, plus 4. And here at the point B, so it should be equal to 3 kilonewton. For the force RA is, so if you simplify, or you can write like this. So it is a combination of point load and UDL. So first we'll calculate the forces without considering this point load. So plus 4, minus 12, plus 4, plus 4, plus 3, plus 6. If you simplify, you will get plus 5. And at this point, at point A, we have minus. So then it will be 0. So these are nothing but the shear forces which are acting on a beam. Shear forces which are acting on a beam. No, now we'll draw the shear force diagram for this. For this again, we'll draw this. We'll draw the figure. Here we have UDL. Here we have UDL. Here we have a support, and here we have support. Here we have support. Here we have a point load. Here we have a point load. Let us call these points as A. Here it is B, C, D, and E. These are the reaction RA and RD. So this is our overhanging beam. I need to draw the shear forces. To draw the shear forces, first I should take a reference line parallel to this, a reference line. Then I need to mark the points. So parallel to this, this will be A, this will be B over here. This point will locate here. This is D, this is E. Clear? Now, shear force at a point E is 0. At the point E it is 0. So at this point we don't have any shear force. Next at point D. At the point D we have, like, between E and D we have this between D and D we have UDL. So UDL, in the sense, whenever we have UDL in the shear force diagram, it should be inclined line. At a point D, we have this UDL along with this point load. UDL along with this point load. At a point D, we have a reaction RD as 12 kilonewton, and here we have converted this as point load. Here we have it is 4 kilonewton. If you see this, here we have 12 kilonewton. Here we have this 4 kilonewton, 12 kilonewton. 4 kilonewton and 12 kilonewton. At a point D, we have shear force. At a point D, we have shear force as -8. That is +4 and -12. +4 and -12 will give you the -8. How to draw? Like, it is a combination of UDL and point load. First, we'll draw from the right side. We are drawing. So first, 4 kilonewton we have. First, we need to draw 4 kilonewton. Next, -12 kilonewton. So at this point, +4, at this point, +4 somewhere here we get +4 kilonewton. Then I need to draw +4 kilonewton. Next we have -12 kilonewton. -12 kilonewton, in the sense this is 0. So this is 4. 4 from here you need to draw -8. Why -8? +4 -8, in the sense this +4 and this +8. Width is 4, this width is 8. So 4 plus 8 should give you 12. Clear? I hope so it is clear now. This is +4, this is -8. +4 -8. +4 -8 will give the -12. I hope so it is clear here. +4 -8 will give the 12 kilonewton, which is acting over here. So whenever we have UDL and point load combination, we need to draw like this. But here between D and D, between D and D, we have UDL. So here we get an inclined line. Here we get inclined line. Now at a point C, what is the shear force at point C? Again, it is a combination of UDL and point load. First, we'll calculate without considering this point load. Then after that, we'll consider that. First, we'll consider like from here to here, this 4 plus 4 plus this 12. 4, 4, 12. This 4, and 12. We'll consider these three forces, then we'll consider this because it is a combination of these two loading. That's why we'll get, if you simplify, minus 4 plus 4 minus 4 plus 4 will give you the minus 4, then this plus 4. So minus 4 plus 4 will give the 0. So while we are trying the shear force diagram, I should keep in mind that I should draw like this. At a point C, we have the loading as minus 4. We have the loading as minus 4. We have loading as minus 4. Then we have plus 4. Then only it will become 0. First we need to draw minus 4. So this is the minus 4. This is the minus 4. Minus 4. Then from this minus 4 to plus 4, again from here if I go plus 4 upward, then it will be 0 over here. That's why minus 4 plus 4 will give the 0 result. It will give the 0 result. That's why we'll here between C and D we have UDL. So between C and D we need to draw a inclined line. Minus 4. This is minus 4. If you go reverse, this will be plus 4. Minus 4 to plus 4. So this is how we have drawn the shear force diagram. Between B and C we don't have any loading condition. So between C and D we get a horizontal line. We get a horizontal line. At point B we have downward force. At a point B we have downward force of how much? 3 kilonewton. At a point B the shear force is 3 kilonewton, which is positive. Positive in the sense somewhere here we get this is 3 kilonewton. So then you need to draw this 3 kilonewton line. Next, at a point A again we have combination of UDL and point load. First we'll consider without considering this RA, then we'll consider RA. For that we have calculated here. Without considering this RA, this is nothing but RA, and these are the forces to the right of this point. To the right of this point we have these many forces, and at this point A we have this reaction force RD. So plus 5 minus 5 will give the 0. First we need to draw plus 5. At point A I need to draw plus 5. So this is the plus 5. Minus 5 in the case. See, this is the plus 5. From 0 to this is plus 5. Minus 5 in the sense from plus 5 to minus 5 it will give the 0 result. From this point, this is plus 5, this is a plus 5, minus 5 in the sense if you come back to this will be the 0. Now between AD we have the UDL, so the UDL in the sense we should get the inclined line. This is the shear force diagram for a given overhanging beam. Next we need to calculate the bending moments. I hope so it is clear. If you have doubt you can comment below so that I can answer your questions. Next we need to draw bending moment diagram. To draw the bending moment diagram I should calculate what are the moments. Clear? First we will calculate the moments. Okay. Here again we will come from the right side. So again if you are calculating the moments from the right side, you should know the sign conversion. What are the sign conversion? Suppose we have a beam like this. Suppose we have a beam like this. If the forces are acting in the downward direction, it creates a hogging moment. It creates a hogging moment, hogging in the sense negative. So it tries to bend the beam in clockwise direction. It tries to bend the beam in clockwise direction. So clockwise we treat as negative if you are considering from the right side. Again, in the same condition, if we have a beam like this, if the forces are acting upward direction, then this let us call this as force P and this as the distance x. This force into distance will give the moment px, and it is in clockwise direction, so we'll take the negative. Here this is force P, this is distance x. This force into distance will give the moment. This is acting in counterclockwise direction. Counterclockwise direction we treat as positive, so it creates a sagging moment. So we consider it as positive. So these two we need to understand. For that, this is a sign conversion to calculate the bending moment from the right side. Now, bending moment at E. At this point, we don't have any point loads. If we don't have any point loads, then the moment about this point is zero. At a point D, at this point, we need to calculate bending moment. At a point D, if I want to calculate bending moment, I should know force and perpendicular distance. To the right of this point D, I have this force 4 kilonewton, which is acting downwards. Downward force is negative. Downward force which creates clockwise moment, so it is treated as negative. So negative 4, this is the force, and distance from here to here to till this, it is 1 meter. So force into distance is 1 meter, so we will get 4 kilonewton meter. This is the moment at point D. Now at point C, moment at point C. At point C, to the right of this, what are the forces we have? We need to see. To the right of C, we have this force 4 kilonewton, which is acting downwards, so minus 4. And from 4 kilonewton, from this to this at point C, the distance is 2 meter plus 1 meter, 3 meter. Next, again, I have a upward acting force. So upward acting force, again, it is positive. So the intensity is 12 kilonewton and multiplied with the distance is 2 meter. Next, I have downward acting force 4 kilonewton and the distance is 1 meter. So if you simplify, you will get minus 12 plus 24 minus 4. You will get at minus 16 plus 8. So you will get plus 8 here, kilonewton meter. At a point C, I get plus 8. Similarly, I need to calculate bending moment at a point. So for that, I will calculate here itself. Now, bending moment at point B. At a point B, bending moment at point B will be at point B. If I'm calculating bending moment at B, I should know what are the moment acting to the right of this. To the right of this, I have minus 4, this force into distance. 2 plus 2 plus 1 is 3. 2 plus 2 plus 1 is 5. Sorry, it is 5. 2 plus 2 plus 1. Next, I have plus this 12 kilonewton into distance is 4. Next I have minus this 4 kilonewton into the distance is 2 plus 1 is 3. Next I have this 4 kilonewton here, negative 4 into this distance is 2. So if you simplify, you will get at a point B, at a point B it should be plus 8 again, plus 8. Next at point A, if you simplify in the same manner, you will get a 0. You will get 0. So these are the values of bending moment. If you don't understand here how the 0 has occurred at a point A, you comment below so that I can make a video on that. Or you can mail at, you can take down the mail ID SYED SAMER underscore ME at cicab.org. Syed Samir underscore ME at cicab.org. Here you can mail so that I can give you the reply within 2 to 3 minutes. Right, clear? Now we'll draw bending moment diagrams. So bending moment, to draw the bending moment diagram, first we'll draw it here itself. We'll draw here itself. So I should know the values here. It is 0 at point D minus 4. At point C it is plus 8. At point B it is plus 8. Then at point A it is 0. Okay. We'll draw bending moment here itself. To draw the bending moment diagram, first I need to take a reference line parallel to the given beam. Parallel to the given beam. So this is the reference line. Then I need to mark the points over there. The first point at point E, these are the points. Look at this point. This has A. This has point B. This has point C. This has point D. This has point E. At point E, the bending moment is 0. At point E, bending moment is 0. At point D, the bending moment is minus 4. At point C, the bending moment is 8. At point B, the bending moment is same. It has 8 plus 8. At point A, the bending moment is 0. Now I need to join these lines. So to join these lines, see, between D and D, we have UDL. So if you have UDL between D and D, I should get an inclined line in shear force diagram and in a parabolic in bending moment diagram. So from point in between D and D, I get a parabola like this, parabolic line, a parabolic line. It should be like this. Between C and D, again between C and D, again I have UDL. So I should get again a parabolic line like this. This is a parabolic line like this between 8 to minus 4. Here between B and C, we don't have any loading condition. We have constant. Again from A to B, we have a UDL. So I get a parabolic curve. Here I get a parabolic curve. This is the bending moment or diagram. Clear? This is the point where bending moment changes its sign. Bending moment changes its sign. So this point we call it as point of contraflexion. Point of contraflexion. We need to calculate this point of contraflexion. That thing we'll see in the next class. If you feel any difficulty in solving these shear force diagram and bending moment diagram, you can mail here. This is my mail ID, SYED SAMEER at sccab.org. You can mail over here. I'll reply for you. Thank you for watching the video.